the properties of X-rays. I have already discussed the properties of X-rays. They are the high energy photons having high frequency and short wavelength, and their energy is calculated by h nu or h over lambda. Their momentum is given by h over lambda or h nu over c. So, fluorescent property, etc. I have already explained, so I will narrate it. X-rays are electromagnetic waves of short wavelength which travel in straight line with speed of light. They are chargeless and are not deflected in electric and magnetic fields. They cause fluorescence in many substances like zinc sulfide, the cadmium tungstate, and the barium platinocyanide. These are some fluorescent materials. They produce photochemical reaction and affect a photographic plate more severely than light. Like light, they show reflection, refraction, interference, diffraction, and polarization. When we say polarization, we are referring to transverse wave character of X-rays. Diffraction means that X-rays have tendency of bending at the corners of the object. Object must be very small. And reflection means striking an opaque medium, and the rays will go back to the same medium after striking the opaque reflector. Then refraction, that is, they show refraction means like light will pass from one medium to another medium. Its tendency is to bend towards the normal. Same is with X-rays. And interference means, that is, if X-rays, they superimpose each other, there is formation of a resultant wave which has low amplitude or the high amplitude, depending upon that how the interfering wave will superimpose. If they are interfering at a point in the opposite phase, we find that the interference will be destructive, and similarly, if the waves meet at a point in the same phase, the interference will be constructive. Amplitude increases. So these all facts are indicated by light, as well as these all facts are indicated by X-ray also. They ionize gases through which they pass. So when we say that they are ionizing the gases, it means X-rays, when strike the gas molecules, the electrons are emitted out from their outer shell. When they fall on matter, now matter means solid, liquid or gas, they produce photoelectric effect and the Compton effect. That is, when X-rays strike a plate, the photons generated move in different directions. That is what the Compton effect. And photoelectric effect will be rarely indicated by X-rays. However, it is indicated in some specific cases. X-rays are highly penetrating and can pass through many solids. For example, they pass through 1 mm thick aluminium sheet sheet while are absorbed by a sheet of lead of same thickness. The penetration power depends on applied potential difference and atomic number of the cathode. It destroys the tissues of animal bodies and the white blood cells. Animal body means that is a human body, or human also that is social animal. Absorption of X-rays. Now we proceed with the absorption of X-rays. That is, when X-rays fall on a metal plate, a part of it is absorbed and part is emerging out from the other side of the plate. So absorption means how much absorption was carried out by given thickness of the plate. For that, we use an equation, I is equal to I naught e to the power minus mu x, where I is the intensity of the radiation emerging out from the plate, I naught is the intensity of radiation falling on the plate, mu is the linear absorption coefficient, and x is the thickness of plate. So, About thickness, the formula will be mu is equal to 2.303 log I naught over I base 10 divided by x. X means thickness, and I naught over I will be obviously greater than 0. The intensity of X-ray beam is defined as the amount of energy carried per unit area per second perpendicular to the direction of flow of energy. More elaborately, we will say that linear absorption coefficient is the amount of energy absorbed per unit thickness of the plate. When a beam of X-rays with the incident intensity I naught passes through material, then intensity of emergent X-rays will be I, and the relation is given as I is equal to I naught e to the power minus mu x, where I naught is the intensity of the radiation falling on the plate, I is the intensity of radiation emerging out, x is the thickness of plate, and mu is the absorption coefficient of X-rays. X is thickness. So if we get the value of mu from this equation, the equation will become I over I naught e to the power minus mu x. And from this we get the value of mu. Mu is equal to 2.303 log I naught over I base 10 divided by x. So unit of mu will be per centimeter, per meter, etc. The dimensional equation of mu will be, that is, m naught L minus 1 T naught. The intensity of transmitted X-rays reduces exponentially with the thickness of material. Therefore, this reduction will be in geometric sequence. The absorption coefficient of material is defined as the reciprocal of thickness, after which the intensity of X-rays fall to 1 over E times the original intensity. At mu is equal to 1 over x, I is equal to I naught over E. The absorption coefficient depends on the wavelength of X-rays. As I have earlier explained, the wavelength of X-rays is not fixed. It depends upon the voltage applied between cathode and anode plate. If the voltage is very high, the wavelength will be very low, and if the voltage applied is low, then the wavelength will be high. The atomic number Z of the material and density rho of the material. Absorption coefficient mu is given by C Z power 4 lambda power 3 rho, where rho stands for density, lambda stands for wavelength depending upon voltage, Z is the atomic number of the target, C is a constant. So now here our main analysis will be that m is directly proportional to lambda to the power 3. Second thing, absorption coefficient is inversely proportional to nu to the power 3, and m is directly proportional to rho. That is, m is directly proportional to density, and m is also proportional to z to the power 4. So next is best absorber of X-rays is lead, while the lowest absorption takes place in air, because air is bad conductor. Now half thickness. The half thickness is very much comparable to half-life. The thickness of given sheet, which reduces the intensity of incident X-rays to half of its initial value, is called half thickness. X is equal to x half, or x half is equal to 0.693 over mu into I over I naught, and this is equal to 1 over 2 power x divided by x1 by 2. So the formulas are the same as that of half-life in radioactivity. Half-life is calculated by 0.6931 over lambda. So here the lambda is replaced by mu. For photographing human body, the parts, BaSO4 is used. BaSO4 is known as the barium meals. So whenever for the internal constitution of the human system, we have to take a photograph or we take X-ray, we first of all give the patient a barium food, and barium food is very sensitive to X-rays. So if number of electrons striking the target is increased, the intensity of X-rays produced also increase. The patients are asked to drink BaSO4, which is known as the barium meal solution for before X-ray examination or before the radiography is carried out, because it is good absorber of X-rays. So barium sulfate is a better absorber of X-rays. Now, there is an example here for the absorption coefficient for the calculation. The absorption coefficient of aluminium for soft X-rays is 1.73 per centimeter. This is the value of mu, that is the linear absorption coefficient. We have to find the percentage of the transmitted X-rays from the sheet of thickness 0.578 centimeters. So thickness X is also given. Now we will apply the formula, that is I is equal to I naught e to the power minus mu X. So this is the formula to be applied, and from this formula we will take the ratio of I over I naught, which is found to be e to the power minus mu X. So it is not necessary to put the value, right, that is e to the power like that. We will first of all, because we are interested to find the value of 1 over e. So what we will do, I over I naught, that is equal to e to the power minus mu X. So e to the power minus 1.73, which is given in the question, multiplied by 0.578. And from this we get the value of I over I naught, that is equivalent to 1 over E. We put the value of E and the value is calculated as 37%. Now there is another example. When X-rays of wavelength 0.5 angstrom passes through 10 mm thick aluminium sheet, then their intensity is reduced to 1/6. Find the absorption coefficient of aluminium. Well, the absorption coefficient is given by mu is equal to, that is I is equal to I naught e to the power minus mu X, and mu is equal to, that is I naught over I base 10 divided by X. So wavelength lambda is given. So to solve this question, mu is 2.303 by X into log I naught over I. Now we compute the values. 2.303 over 10, that is 10 mm. We have taken the thickness in millimeter. Now we have to make calculation only in millimeter, not in centimeter. So it becomes log 6 base 10 in accordance with the question. After putting the values, now if we wanted to find log 6, it should be log 3 multiplied by log 2. So it will become log 3 plus log 2. Log 3 can be taken as 0.4771 and log 2 can be taken as 0.3010. So in all, we will put up all these values and we will get the linear absorption coefficient, which is 0.198 per millimeter.